Alright, so we have this sort of oddly defined function, and we want to use it to find a counterexample to prove that continuity of the derivative is absolutely necessary on the hypothesis of theorem 2-11. Okay, so we have this function. So let's see here. We want to prove something about. If you have your function in theorem 2-11, it needs to be continuously differentiable at a particular point. So if we look at this function, well, the point where things are defined differently is 0. So it should make sense that the point that we're going to be looking at is 0. And so the first thing we need to do is prove that f is in fact not continuously differentiable at 0, but that it is differentiable, just not continuously differentiable. Okay, so the limit as x approaches 0 of f of x is going to be what? Well, if we look at this thing, of course, x over 2 is going to go to 0. Then if we look at x squared sine of 1 over x, I talked about this in exercise from the previous section, but you can use the squeeze theorem to prove that basically sine of 1 over x is going to oscillate back and forth between -1 and 1 as x approaches 0, but x squared is going to approach 0 at a faster rate. And so by the squeeze theorem, you can actually prove that the limit as x goes to 0 of x squared sine of 1 over x is actually 0. And so the limit of this function is 0. So f prime at 0 equals 0. Because if you remember what the definition of the derivative is, here, let's actually write out one more just to make it a little more clear. So we're going to have 1 over h, and then we have f of 0 plus h minus f of 0. And now f of 0 is 0, and the limit as h goes 0 of f of h is 0, and so the numerator here is 0. And so this limit is obviously going to be 0 then. Okay, so the derivative exists at 0. Now for x not equal to 0, we can actually compute f prime of x directly. So derivative of x over 2 is going to be 1/2. Then derivative of x squared sine of 1 over x, we're going to have to use the chain rule. Or no, product rule. So we're going to have 2x sine 1 over x. Then we're going to add x squared. Then we multiply by 0. So we have to apply the chain rule now to take the derivative with respect to x of sine of 1 over x. So derivative of sine is cosine, so we have cosine of 1 over x. Then we have to multiply by the derivative of 1 over x. So the derivative of x to the -1, you bring down the -1, and then the exponent becomes -2. So minus x to the -2. So this is going to be 1/2 plus 2x sine 1 over x minus cosine 1 over x. And so f is in fact differentiable on R. However, if we take the limit as x goes to 0 of f prime of x, well, 1/2, that's just going to go to 1/2. 2x sine of 1 over x. Again, we can use the chain rule, I believe. No, I mean squeeze theorem. Right, because sine over x is going to be between -1 and 1. So multiplied by x, and it's going to be between minus x and positive x. Take it to 0, and you squeeze it to 0. So yeah, so second term will go to 0, and then the third term, cosine of 1 over x, that's going to oscillate. So this limit does not exist. So f prime is not, even though f prime is defined everywhere, it's not continuous at 0. So f is not continuously differentiable at 0. And so this is in fact the point that we want to look at. So what does theorem 2-11 say when it applies? It says that if you have a function at a point, then you can invert the function within, first of all, you can invert the function within some neighborhood of the point, and furthermore, it gives you, that inverse is differentiable, and it gives you a formula for the derivative of the inverse. All that stuff is not, those later things, those aren't the things that we're going to run into problems. We're going to run into problems just with inverting this function in a neighborhood of 0. So if theorem 2-11 were to apply to f at 0, then f would need to be invertible in some neighborhood of 0. All right. So f would need to be 1-to-1 in some neighborhood of 0. Because in order to invert a function, it needs to be 1-to-1. Because basically invertibility is right. Anytime you have a 1-to-1 function, you can invert it. And of course, this is very clear when you think about bijections, because bijections are functions which are 1-to-1 and onto, and anytime you have a bijection, you can just straight up invert it. But even if you just have a 1-to-1 function, to get a bijection, you can just restrict the range of the function to the image of the set on which the function is 1-to-1, and then you get a function which is 1-to-1 and onto, and so you get bijection, and then you can go ahead and invert it. Okay, so anyways, point is, f would need to be 1-to-1 in some neighborhood of 0. To prove that this cannot happen, so of course what we're going to end up proving is that f is not 1-to-1 in any neighborhood of 0. And that's basically because f oscillates too much. But anyways, let's prove this rigorously. Let I be any open neighborhood of 0. So I, you can write it as like r comma s, where r is a negative number and s is a positive number, and so it'd be the open interval from r to s. Okay, so basically here, I think I'm going to go ahead and write out a picture of what this function looks like. So what does this function look like? Well, if you think about it, you have x over 2 plus x squared sine of 1 over x. So x over 2 is going to look sort of like a line like this, maybe? So this is x, this is y. And then if you take a function and you start here, it might look something like this. It's hard to tell, but basically f of x, it's going to be sort of, it's asymptotically going to look like x over 2 as you approach the origin, but before you approach the origin, it might, okay, so it might look more like this. Because when you're far from the origin, you have this x squared sine of 1 over x term, which is oscillating things. And so if you look like maybe over in this region, it's obvious that f is not 1-to-1, because if it goes back and forth, then you're going to, like, if you take like just some horizontal line, you're going to hit multiple points, like right here and right here. And so then it's the case that f is not 1 to 1. But we want to prove this but if you look closer to the origin here, it's not entirely clear that f is in fact not 1 to 1. So what we want to do is we want to... The main idea that I use to sort of look at this is, so we have this line x over 2, and we know that because sine of 1 over x is going to be 0 infinitely many times as you approach 0, as you approach the origin, you're going to hit this line a whole bunch. And so we want to use that to our advantage. And when you go between these points, it will probably look like a sine function. Now you've got this x squared term here, which might mess things up, but we'll have to see. So if you look here, if you take this point, let's call this point here A. So at x equals A, if you go enough to the left, you'll hit another point right here, where the function takes on the same value as f of A. And so then the function is automatically not 1 to 1. However, it's not entirely clear that this is what this function looks like. It could be the case, for example, that maybe it oscillates, but it oscillates not very much in a way that it's like actually turns out to be a strictly decreasing function, at least perhaps in some neighborhood of the origin. But we want to prove that that's not the case. And so what we actually want to do is, if it turns out that the derivative of f at A here is negative, then it must be a little bit larger over here, and we're going to use that to our advantage. Okay, so now hopefully the visual description didn't make things more complicated, but from here on out we can actually look at the symbols, and from the symbols, if you want to, you can sort of backtrack and get the visual interpretation or visual intuition. So anyways, I is some open neighborhood of the origin. We want to choose some point A here like I've drawn. So what we're going to do is we're going to choose a natural number n large enough such that the number A, which we will define to be 1 over 2 pi n, is an element of I. And this is possible because if you take the limit as n goes to infinity, then A will go to 0. And the reason that this matches up with the picture that we have is that if you evaluate sine at 1 over A, you're evaluating sine at 2 pi n, and so it's going to be 0. Now, the reason that I chose 2 pi n here for a specific reason, but we'll talk about that in a bit. Okay, so then, as I just mentioned, sine of 1 over A equals sine of 2 pi n, which has to be 0. And now the reason that we chose 2 pi instead of just pi is that this guarantees that cosine of 1 over A, which is cosine of 2 pi n, is positive 1. So thus, we have f of A equals, well, let's see, if we remember f of x equals, we've got 0, and then we've got x over 2 plus x squared sine 1 over x. F at A is just, well, sine of 1 over A is going to be 0. And so we just have A over 2. So f of A is A over 2. And f prime of A, if we remember what the formula for this is, actually it's just up here a little bit if we can just scroll up just a bit. So we've got 1/2 plus 2x sine of 1 over x minus cosine of 1/2, or cosine of 1 over x. So f prime is going to be 1/2. And then 2x sine of 1 over x, well, sine of 1 over, or 2a sine of 1 over a, sine of 1 over a is going to be 0, so that's going to be 0. We're subtracting cosine of 1 over a, so we're subtracting 1, which is minus 1/2 which is less than 0. So now we're in business, because that's what I talked about for this function here. We wanted the derivative of f at a to be negative so that we can go a little bit to the left and get a point where f is larger, where f evaluates to a value larger than f of a. Okay, so the fact that f prime of a is negative, therefore there exists a b which is less than a, such that b is an I, and f of b is greater than f of a. And let's see here. So in fact, since the derivative of f at a is negative, this point b here can be arbitrarily close to a. And so, in particular, we absolutely need to be able to choose b to be an I, because a is a strictly positive number, so we can choose b to be strictly positive, which means that it's an I, because the interval I extends to the negative real line, at least a little bit. Okay. So, now what we're going to want to use is we're going to want to use the intermediate value theorem. And so, if we want to do that, then we're going to need to find a point where f evaluates to a number which is less than. So let's see here. Just let's redraw this picture a little bit, and of course I completely messed it up. But yeah, so we've got, this is our picture. So this is going to be b. Now to get a value of x such that f of x is less than f of a, we're going to choose this point here. So actually no, we're going to choose this one. We're going to choose the next point at which sine of 1 over c is going to be the largest number smaller than a, such that sine of 1 over c is 0. So that is going to be, we take 1 over 2 pi n, which is a, but then we add an extra pi to it, because that's the next place where sine of 1 over, that's the next value of x where sine of 1 over x is 0. We're going to choose this so that c is going to be an I, certainly, because it's a positive number, which is less than a. So it's a positive number less than a, so it must be an I. And f of c is, again, going to be c over 2, because c squared sine of 1 over c will evaluate to 0, and c over 2 is less than a over 2, which is f of a. So now we can go ahead and apply the intermediate value theorem. So by the intermediate value theorem, again, I'm assuming that we can just use the intermediate value theorem, even though I don't remember if we've proved it at all. If you really want to prove it, you can go read Baby Rudin, but yeah, I don't think they would expect you to actually prove the intermediate value theorem in this exercise. Okay, so since f of c is less than f of a is less than f of b, there exists some value d which is between c and b, such that f of d equals f of a. Wait, is this mean value theorem or? Yeah, this is intermediate value theorem, of course. And this relies on the fact that f is continuous, which it is. Yeah, because it's comprised of continuous functions. The only place where it's not continuous is at the origin, but here we're away from the origin. No, even at the origin it's continuous. Right, anyways. So we have this point D. Now I said between C and B. In this picture that I've... Okay, so D would be like right here. So here it would be, okay, so, and that's going to be where A, B, D, C. Okay, so here D is greater than C and less than B. Of course, if you choose B to be close enough to A, then you can guarantee that B is greater than C, but that's not absolutely necessary. It could be possible that it like oscillates a whole bunch more than we're expecting. And so B could actually be even further to the right than, or further to the left than C, but it doesn't really matter. So I just wrote between C and B rather than C less than D less than B. But anyways, it's not really important. So the fact that D is between C and B implies that D must be in I. Well, in fact, that's because D is going to be less than the larger of the two, which is going to be less than A. And D is also going to be greater than... Here. So C and B are both positive numbers, so they're greater than 0. So, and D is greater than the smaller of the two, but it's also less than the larger of the two, which is less than A. And so D belongs to the open interval from 0 to A, which is a subset of the interval I. So F cannot be 1-to-1 on I. So F cannot be invertible on I. Hence, theorem 2-11 fails if we do not assume that F is continuously differentiable at this particular point. So yeah, it took a little bit of work to get this. I sort of like problems like this because you can use visual intuition. I personally like functions from R to R better than functions from Rn to Rm or whatever, because I can use more visual intuition like this. But yeah, this sort of highlights an important thing in math, where we have a theorem that we can prove, and you use a whole bunch of hypotheses, and you prove a theorem. But you want to ask, were all of these hypotheses absolutely necessary? And sometimes in doing the proof, it becomes clear that, yeah, this hypothesis was absolutely necessary for this step of the proof, but sometimes it's not always as clear. So it's always useful whenever you can remove a hypothesis of a theorem and prove that the theorem no longer holds. Because if you remove a hypothesis of a theorem, one of two things is going to happen. Well, one of three things, I guess. Either the theorem is no longer true, in which case you know that theorem is absolutely necessary. Or you actually can prove the theorem, which means that hypothesis was not necessary, and so then you've come up with an even stronger proof, a theorem that applies in a larger range of situations, and so it's a strictly better proof. However, another thing that can happen is you don't know. And I don't know, I think that's And something that a lot of mathematicians struggle with is like you want to see like is this theorem still true if we remove this hypothesis? And generally, a lot of times, like trying to prove or disprove a theorem, removing a hypothesis, it can be hard. There's no way to know if it's going to be easy or extremely difficult. But yeah, this is an important task in mathematics because it allows us to refine our theorems and make sure that we're getting the most that we can out of our hypotheses. But yeah, that's all that we need to do for this exercise, and so we're done.